Hello everyone, welcome to my next video, Kinetics of protein binding. So we were discussing about the distribution of drugs. In distribution we are discussing about the protein binding of drugs. In protein binding we discussed what is protein binding and what are the significant effects and the clinical effects of protein binding and the different types of plasma proteins responsible for binding of drugs. And today we will discuss about the kinetics of protein binding. It is very important as clinically as well as exam point of view also. This may come in 5 marks or even 10 marks. Long answer also, this kinetics of protein binding might have been asked. So kinetics of protein binding. Generally protein binding kinetics will be related to Michaelis-Menten's equation, because here proteins are also limited in number, so they can, that is finite number of proteins are present, so the drug which can be bound, the number of drugs that can be bound to that finite number of proteins will saturate the system. So further increase in drug concentration may not change the protein binding of drugs. So protein binding are saturated process, or the capacity is limited in case of protein binding, which can be explained by this Michaelis-Menten's equation. So to explain this kinetics of protein binding, we should know how the protein and drug bonds. So P is the protein and D is the drug. The protein and drug binds to form a protein drug complex. P is protein and D is drug, and it forms protein drug complex. And the stability constant or the association constant involved here, it is Ka. So we have mentioned equilibrium type of equation arrow here, because this protein binding is reversible in nature. In first class of protein binding, I already discussed this. Protein binding is reversible. This protein and drug binds to form a complex, and this complex can be further dissociated again to the free form of drug. That is why this type of arrow is used, which explains the reversible form of the complex formation. So protein binds with drug to form a protein drug, and this association constant, according to law of mass action, it can be written as Ka is equal to the square bracket of the product, that is concentration of the product. Here the product is complex, divided by the product of the concentration of reactants, which is P and D. Reactant here is P and D. So the square bracket explains the concentration. The concentration of complex to the concentration of protein and drug is its association constant. This is according to law of mass action. So the equation became like this. This is equation number 1. Now just exchange this equation. So PD will be equal to Ka into P into D. This is equation number 2. Just we have interchanged the equation, and PD is equal to Ka into P into D. Equation number 2. Now the total protein concentration. How much total protein is present in the plasma? It is the free protein present plus the protein that is bound with drug is the total concentration of protein. How much the total concentration of protein, which is free form and the bound form. So the free form of protein is written as square bracket of P, and the concentration of bound protein is written as the concentration of PD, square bracket of PD. This is the free protein and this is the bound protein. Bound protein, and this is the total protein present. So the total protein is nothing but the sum of free protein plus bound protein. So this is equation number 3. So R, now introducing a new term R. Now what is this R? Number of moles of drug that binds with the total plasma protein. So total protein that is present in plasma, how much number of moles of drug has been bound can be mentioned as this small r. Small r is nothing but number of moles that is bound to the total drug. Say for example, we have total protein is about 30 and the number of moles of drugs bound with that protein is 30. So this is known as R. So out of the total proteins, how much is the number of moles of drug bound can be written as R. So it can be written as the total protein concentration, among that how much drug is the bound form is written as PD. So out of the total protein, how much is the bound form as R. So we can rewrite this equation for including the PD as PD can be written according to the equation. So use equation number 2 and equation number 3 for writing PT. For writing PD, we are going to use the equation number 2 and for writing PT, we are going to use the equation number 3. So PD can be written as according to the equation 2 Ka into P into D divided by PT can be written as P plus PD. But PD is already Ka into P into D. So this PD also can be written as Ka into P into D. So there is a common term which can be taken outside, which is P in denominator. So R is equal to Ka into P into D upon P is common. So I have taken that outside. Inside this P has been taken out outside. So it is 1 plus Ka into D. So P and P from numerator and P from denominator get cancelled and the remaining equation is R is equal to Ka into D upon 1 plus K into D. Now this is the protein binding kinetic equation which explains for a one binding site. But we already discussed proteins have number of binding sites. So this equation holds good only for the proteins having one binding site. If we have n number of sites, then the equation will further change into n into KAD upon 1 plus Ka into D. This is the final kinetic equation where n is the number of binding sites. So this equation explains the protein binding kinetics and the drug concentration. So how the protein binding kinetics will be affected at low concentration and at high concentration after saturation of protein binding sites, all will be explained by this equation, which is similar to that of Michaelis-Menten's equation. Now here there are two constants or the parameters which has to be determined, that is n, capital N, which is the number of binding sites available for binding of drugs, and Ka is the association constant or the stability constant of the complex formation. This can be explained, or the binding affinity, how much the affinity of the drug binds with that of protein can be explained by Ka. So association constant and N have to be determined. So we have three methods for this determination. One method is direct method of determination of this N and Ka, and we have the second method which is using scattered plot or scattered equation. So we have the second method using scattered plot or scattered equation, and the third method is by using double reciprocal plot. So there are three methods available for determining this N and Ka. N and Ka can be determined by these three methods. One is direct method and another is using scattered plot, and the third method is by using double reciprocal plot. So let's explain the first method of determination, N and K. So we are going to plot a graph using R in y-axis. So R, that is number of moles of drug bind with the total protein R, is plotted in y-axis, and the concentration of drug in x-axis. So when you do or perform experiment of protein binding of drugs and you are increasing the concentration of drug with that of the protein, so you are observing the following results. How the results will be when you plot the graph. So when there are increase in concentration, that is at low concentration, as you increase the concentration of drug, the binding also increases, but not increased continuously up to certain extent. Once it reaches the maximum, after that increase in concentration leads to remaining the constant in the protein binding. So protein binding increased with increase in concentration of drug at low concentration, but it is up to certain point. When there was maximum increase in protein binding took place, after that even you increase the concentration of drug, there was no change in the protein binding. As like I said, in carrier mediated transport, protein is also limited number. Say for example, only 50 proteins are present and you are just sending 5 amount of drug to bind. That will bind. Now you are increasing the concentration and sending 10 drugs. Now it binds. But when it goes beyond 50, because sitting space or the binding place available for the drug is only 50. If it goes, when in the 50 binding sites will be saturated with the drug, when you send more and more drug, there will not be any change in the binding of drugs, because the binding sites have been already saturated as explained by this graph. Initially the binding increased. Here the saturation, that is that many binding sites are only available. So after this, when you increase the concentration, the protein binding remained same, that is R value remained same. So you know here the maximum rate occurs, that is protein binding occurs. Where the maximum protein binding can be occurred? It is at the maximum binding site. So the maximum point where the constant starts, that concentration when you extrapolate to y-axis, where it meets the R, will give you the value of N, because N is the number of binding sites. This much number of binding sites are totally present. That is why the concentration or the protein binding is increased up to that. The maximum level increased up to that. After that it remained constant because saturation took place. So where the maximum took place and after that constant value remains, that when you extrapolate to the y-axis will give you the N value. So to determine the Ka value, so we have to determine N and Ka. N we have determined from this extrapolating the maximum value to R. Now to determine Ka value, now we have determined R, now take the value of R by 2. So consider R as R by 2. So this R is R by 2. So you are getting the value of Ka here. How we will get the value of Ka here? Because now you place the value of R as R by 2 in this equation. Now we will make this equation as equation number 5 and 6. Put R is equal to R by 2 in equation number 6. Now R by 2 is equal to N into Ka into D upon 1 plus Ka into D. Now just rearrange this equation. So this will come this side. So it will be like R is N by N. So the R can be written as, R, we have taken R by 2, it can be written as N by 2. So this is the value of R where we got N. So we are taking the half of this N, which is N by 2. So we are placing R as N by 2. So write the value of R to be N by 2. So N will get cancelled. So the remaining value will be, this goes this side, 1 plus Ka into D is equal to 2 into Ka into D. So this will be 1 is equal to 2 KAD. When this goes this side, my plus will become minus KA into D. 2 KAD minus 1 KAD is equal to 1 KAD. So it is, so KA will be equal to 1 upon D. So when you just take half of this, the maximum value is half of the maximum value is n. When you take half of this and reduce this half to n, and when you extrapolate this curve and you get here the 1 by Ka. So reciprocal of this will give you the Ka value. This is direct method using the equation. Whereas in scattered method, you just rearrange this equation, that is just multiply here. So r into 1 is r plus Ka into D into 1 is R into Ka into D is equal to N Ka into D. Now keeping R on one side, so R is equal to N Ka D minus this plus will go this side, so R Ka into D. This will be rearranged like this. Now see, it is similar to that of straight line equation. What is now straight line equation? It is y is equal to mx plus c. So see, this is similar to y and this is x and this will be m. Sorry, here it is the slope. So this will be x and this will be m and this will give you the c. So we have R is equal to N KAD minus R KAD. Now you can plot the graph of R and D on. So a D also can be taken common. So D can be taken this side. So R upon D is equal to N Ka minus R Ka. So we can further reduce this equation and we can make it as Y and this is M and this is X and this is C. So Y is equal to Mx minus Mx plus C. So we can plot R by D, that is Y-axis, and D in X-axis. So X is R. So R by D versus R will give you the negative slope straight line. Since the slope is minus, the equation, the straight line will be decreasing. It will be in reducing way, whose slope will be Ka. So we can determine Ka from the slope. And when you extrapolate this to y-axis, you will get n Ka. So we already calculated Ka. So n can be easily calculated from the intercept. So this is the scattered method. What we are doing in scattered method, just we have rearranged the equation. That is, we just multiplied this here and took D common outside. So R by D is equal to n Ka minus R Ka, which is similar to straight line equation. So this is y. And placing R in x-axis. So y is R by D, x is R. So you will get a negative slope. So the line will be from above to below, that is decreasing with the negative slope of Ka. So from slope we can determine Ka value, and as we know Ka value, from the intercept we can determine the n value. Now the next equation by which we can determine this n and Ka is double reciprocal. What does it mean? Just take reciprocal on both sides, left hand side and right hand side. So when you take reciprocal on the left hand side, it is of 1 by R. So when you take reciprocal on this right hand side, it will become 1 upon N KAD, that is just taking this 2 and then this 2, plus KAD upon N KAD. Now KAD will get cancelled. So 1 upon R is equal to 1 upon N KAD plus 1 upon N. Again, this is similar to the straight line equation. This can be mentioned as Y is equal to 1 by D can be mentioned as X, and this will be M and this will be C. So when you plot the graph, that is y-axis is 1 by R and x-axis is 1 by D. Just see the first equation, just opposite. Here we are using R and D, here 1 by R and 1 by D, reciprocal of the first plot. This is direct and this is reciprocal plot. So 1 by R versus 1 by D. Here you are getting the carrier mediated transport, like that is capacity limited type of plot. But here it is similar to straight line equation. So you will get a straight line whose intercept to the y-axis will be of 1 by n. So first of all you have to determine the value of n using the intercept and placing that value in the slope, because we know already n value, so you can determine Ka from the slope. Here you have to determine intercept first, because you have the only one constant. Here two constants are involved. So first of all determine n, then from using n and the slope value you can determine Ka. This is about the kinetics of protein binding. Kinetics of protein binding can be explained by this sketched equation, and from this you have to determine n and Ka value by direct plot method. Direct plot means using this equation directly you have to plot R in x-axis and D in y-axis. Then you will get a saturated type of plot. Initially increased, that is straight line, and after maximum it will be constant. And from that is the maximum where it is the protein binding achieved. It is the number of binding sites. This explains the number of binding sites. And take n by 2 value and place R is equal to n by 2. So you can determine the another Ka also. And in second sketched plot you have to just rearrange, that is multiply this here and then take D common outside, and then with the negative slope and intercept you can determine n and Ka. And lastly double reciprocal plot, where you have to take the reciprocal of both the sides, then you can determine from the positive slope and intercept you can determine n and Ka value. Now in my next video we will discuss about the factors affecting protein binding of drugs. Thank you.